galaxies, constellations, stars, planets. The universe appears to be infinite, but starting from his tiny dot in one corner of the Milky Way, man is beginning his conquest of it. After his first trial steps, he will one day walk the moon. We can marvel at such exploits, even as we realize that chances are slight that man will venture personally beyond his own solar system. It is a long way to the stars. One of the slenderest things on our small planet is spider silk. That's why these fine threads are used for crosshairs in delicate optical instruments to study the stars. Spider silk is so fine that 1 pound would circle the Earth. To reach Alpha Centauri, the nearest star beyond the sun, would require 500,000 tons of silk, enough to fill a train 150 freight cars long. Only by the science of astronomy can we leap across this vastness and, by our eyes, and with special scientific instruments, analyze the elements and atomic structure of distant suns. The sole source of knowledge of objects beyond our solar system is electromagnetic radiation. When the spectroscope was invented, we found we could analyze matter by its radiation. Every chemical element creates a unique set of special lines that we can compare with others. Thus, we can deduce that the entire universe is made up of elements similar to some of those we find on Earth. We see some radiations as colors, but despite the fact that we receive almost all our knowledge through our eyes, the visible spectrum is a narrow one. We might see many new colors if we could see into other wavelengths, such as radio waves, infrared, ultraviolet, X-rays, and gamma rays. And the light invisible to us can tell us much about the mysteries of space. Already, this invisible light has led us to a new understanding of the universe and provided unsuspected puzzles for our solution. The envelope of air which protects life on Earth also screens out or absorbs the starlight in this portion of the spectrum. And it is these invisible radiations that could one day tell us how stars are born and die, and how the universe was created. For earthbound astronomers, the challenge is tantalizing. Telescopes on brief rocket flights have brought us hints of entities we never knew existed. And balloon flights have lifted telescopes 8 miles into the air to take some of the clearest photographs of the sun ever obtained. From earthbound views like this to this. Yes, it is beyond the air that we must go if we seek a clearer image of the heavens. Above distortion that makes the stars twinkle, above the blotter of air that absorbs the ultraviolet, the X-rays, the gamma rays, on which much of the study of starlight depends. We need a solid platform, hundreds of miles out in space, from which to make our studies. Not a rocket, not a balloon, but an orbiting astronomical observatory. And that is what has been developed by scientists at the Goddard Space Flight Center, where Dr. James Kuparian headed a group of distinguished astronomers. To know the stars, we must capture starlight, light that is cut off forever from human eyes on Earth. For this, we need special telescopes. There are such telescopes, and here is Dr. Arthur D. Code, who helped design one of them at the University of Wisconsin.
The radiation that comes to us from celestial objects spans the entire electromagnetic spectrum, from the long radio waves through the infrared and visible light into the X-ray and gamma ray region. The Wisconsin telescopes are designed to observe in the ultraviolet region beyond the range of visibility of the eye. Space contains not only many old stars like our sun, a few billion years old, but young blue stars, only a few 100,000 of years of age. These young, hot stars give off most of their light in the ultraviolet, a region which does not penetrate the Earth's filtering atmosphere. The Wisconsin telescopes will be able to see these hot young stars. They will measure the energy distribution and the intensity of light from young stars, something never before possible. From these studies and many more, we hope to learn more about how stars are born, age, and die, and how matter is reborn into the universe.
This telescope was invented in the 17th century by Monsieur Cassegrain. Medieval, but a modern version will aid man's knowledge of space. Dr. James Kuparian of the Goddard Space Flight Center has, with the help of other NASA astronomers, devised a new way to use Cassegrain's ancient telescope.
The Goddard telescope system has been developed by us to explore ultraviolet radiation of stars in a manner somewhat similar to that of the Wisconsin telescopes. The emphasis, however, is on increased spectral resolution. With the Goddard telescope in space, we can sample radiations emitted from within our own galaxy and compare them to emissions from galaxies tens of millions of light years distant. It's an exciting prospect. With the OAO, man will go a long way toward solving the mystery of the creation of matter.
Through our new window on the universe, we shall search the stars in many ways. An early project will be the mapping of the entire sky by ultraviolet light. In charge of making this unique celestial map is Dr. Fred Whipple.
The new map of the universe, which will be very different from these maps, will be made by a telescope. With 4 such ground-controlled telescopic cameras, we intend to make an all-sky map in 4 separate ultraviolet colors. In addition, we plan to catalog more than 30,000 very hot stars, much brighter than the sun, many times more than astronomers have previously recorded in the ultraviolet.
Among other objects, an ultraviolet map of the sky will study pockets of interstellar gas and dust clouds. Some are dark, some almost invisible from Earth. These vast clouds in space may hold clues as to how stars are born. An OAO project, developed in the Space Telescope program of Princeton University, will investigate these provocative dark areas. Dr. Donald Morton describes it.
This telescope can be used for many different kinds of observations, but at Princeton, we have a particular study in mind. Not all clouds are as dark as this one in Orion, but it is apparent that the space between the stars is not empty, but filled with great clouds of dust and gas. As starlight travels towards us, the atoms in these clouds absorb part of the spectrum. By observing these areas in ultraviolet light with our spectrometer, it's possible to deduce the density and chemical composition of the interstellar gas. All the telescope packages will be working in the same range of wavelengths, but there will be a difference in the sharpness of resolution. For example, the Smithsonian and Wisconsin telescopes will take the initial broad approach with low resolution studies in bands 500 to 10 angstroms wide. The Goddard telescope will examine this same radiation with medium resolution in bands from 10 angstroms down to 1. And for the Princeton package, there remains high resolution, down to 1/20th of an angstrom. Astronomers have long believed that new stars are formed by the condensation of interstellar gas and dust. With our OAO, we hope to determine the density and chemical composition of this tenuous material, and then we may be able to better understand the process of star formation.
This satellite, the OAO, is the biggest and most complex unmanned satellite in the NASA program. Built by the Grumman Aircraft Corporation, it is basically a shell into which various kinds of telescopes can be mounted. When it has been placed in an orbit 500 miles beyond the Earth, this space observatory will give us eyes to see into regions until now invisible to man. Launched by a Centaur rocket, the OAO sheds its protective fairings in space. The OAO powers itself through solar panels, storing electrical energy derived from sunlight. Once in orbit, it relies on solar sensors and star trackers to stabilize itself. Then it opens its eyes to look through a new window in the universe. With each succeeding year, a new OAO will be orbited. The first one in space carries telescope packages in both ends. From a ground control station, men reach into space 500 miles to point the OAO toward any part of the sky they wish to study. Precision is such that the OAO could fix on the eraser of a pencil 100 miles away. Observations can be stored by magnetic memory, and all information flashed to Earth within seconds. Recorded as numerical data, starlight images can be translated into pictures by the trained scientists. The OAO will be another significant advance in astronomy since Galileo aimed the first telescope to prove the Earth was not the center of the universe. From the time when prehistoric man wondered at the bright pinpoints in the sky, astronomy has developed as a challenge. The OAO, the Orbiting Astronomical Observatory, will extend man's range of vision across the universe. Man, on his tiny planet, a sand grain on the shoreline of the seas of infinity, longs to find out what the stars are, why they are there, how they came to be there, vast in the immensities of space that may or may not have a beginning or an end.